Okay, guys. For the quadruped robot I have in my lab, may have seen this video on the YouTube. The company in China is a Go1 company, and they are making based on the MATLAB interface plus Python. They are working with the robot. So you have to be expert of MATLAB as I'm doing right now with the control. And when it comes to robotics, you can do this, or you can go to the Python. Both works. Okay. So let us continue our problem. It was inverted pendulum, and we said the length of pendulum was 1 and m was 1 kilogram. After the class, I tuned more for Kp, Kb, and Ki. You saw that with the previous version, it was almost 50 seconds that it goes to desirable angle of the pendulum. Here was 60 degrees. That's right. I said 60-degree desirable angle, right? And but it is a trade-off, guys, um, between the control command U or torque in Newton meter and the time of the operation. So I tuned more by increasing Kp, Kd, and Ki. And you know, this is the, just refreshing your mind, this is the error signal. Now you know that this is the E dot, and this is integration. Sum is integration E dt. And you know, these are the global parameters that we defined here. Global parameters. Oh my, sorry. Yeah, thanks for letting me know. Okay. So, so I have to say again. So, after the class, in the previous class, I tuned more Kp, Kd, and Ki to higher values, okay, to shorten the transient response to 5 seconds. In the previous tuning that we did in the previous class, it was 50 seconds, but it's a trade-off. I'm going to show it now between shorten the transient response and the control command or torque in Newton meter. So you have to be very careful, because in reality, when you apply to a robotic problem or whatever it is, maybe your actuator that sends the control command becomes saturated very easily, or going to damage that. This is out of range of the torque of that. Okay, assuming that your actuator is fine now, I increased after the class Kp, Ki, and Kd. Okay, and you saw to push the inverted pendulum to 60-degree, and this is the error signal, if you remember, E dot, and this is the I part. Sum is integration E dt, and we just define U for linearized system Kp E plus Kd E dot plus Ki integration of E. That's right. And this is for plotting. And this counts means for global that you're gonna plot. See here, we define here. And this is the state space that you know it for the linear one. And now if I run this, guys, and I made this from beginning of the class. I changed the interpreter to LaTeX to save time in the class, to show it very professionally, like as now you know it. That's right. I taught you previously. So if I run this, guys, you see that here we go. You see that first, the initial torque is 1000 Newton meter. Is too much. So when you're tuning your gain, not in the PID control. If you go to a nonlinear control scheme, name it from sliding mode control to adaptive control to delay control to whatever MPC control. So you have to be careful that this is not out of the range of your actuator that you have in your robot or you have in any system. Okay, this can be a saturated signal. Okay, assuming that is not assuming. Okay, and I just want to show you. See that now increase to at 8 seconds, inverted pendulum from vertical position goes to 60-degree. See, almost goes to, at 8 seconds. If I decrease these gains for the PID controller, your U becomes lower, obviously, becomes, if you remember, was 70, 80, but the transient response settling time is much higher, is 50 seconds, like that. Okay, so the trade-off. You as a designer of controller, it's you that you have to decide. If your actuator can't tolerate that, so based on the requirement of the system or bus requirement, you can't tune this. Now it goes to 8 seconds. So you see, this is error signal, guys. So error signal after, let me zoom in, exactly after, say, 10 seconds, almost goes to 0. That's right. Huh? So that. So how to add a disturbance to the system? Because we have I controller. I'm going to share this with you. I controller, and you know that the I controller function is to remove the steady state error signal and reject the disturbance. It's very easy. I'm going to say if time is greater than 2 seconds and time is smaller than 4 seconds, disturbance is, I don't know, 10, and else disturbance is 0. There we go. I want to apply disturbance, guys, before running. Here. Oh, okay. I'm going to show it to you. So you have to add disturbance for linear system here. So here, D. I just added D. Beside. Now I'm running that. Oh, you see the effect of that here? Disturbance. So the controller tries to overcome that. And let's see what's happening. Oh, here we go. See? Between 2 and 4, you see? Such a... Here we go. See here? 2 and 4. Oh, let me magnify it. There we go. See? Actually at 2, I have a step disturbance. But PID controller, I part, reject disturbance. I want to make it bigger, guys. Let's say, I don't know how much is that. Where's that? So this is disturbance. I'm defining. This is how we define disturbance in MATLAB coding. Just by if command. Okay? Let's say 50. Make it more visible. Here we go. See the effect of that in U control command? And we're gonna see that here. Here we go. See? At a 2 second, huge disturbance, but I control rejects that until 4, and then goes again to 60 degree. Are you following me, guys? Everybody? Huh? Even you can have two. You have two disturbance. Else if t greater than 5.5 seconds, d is minus 40. Minus 40 means this disturbance is in the direction of the rotation, is coming down, but this is in the opposite direction of that. Okay. Else if and t is smaller than 6. So now we have two step disturbance on the system. Here we go. See, 1, 2. See the direction of the control input here tries to remove disturbance. This is we're gonna see it here, obviously. Here we go. See, between 5 here was in the direction of rotation. Here is the opposite direction of rotation. See, between 5 and 6. But again, the I controller rejects disturbance and goes to 60. Okay. Yes. So, so you mean that, let us say, it's a good question. Let us say after this, your D is ramp. That's right. Your D is ramp between so and gradually increasing with time. That's right. See what I'm saying? So let us see if these gains that I tuned after the previous class reject that disturbance because this is ramp. That's right. Y is equal to T. Remember? Ramp. Right? This is a step. Let me write this. This is step with the value of 50. Okay. Step disturbance. And this is ramp disturbance because I'm going to share this file with you today. Okay. Let's see if these gains rejects that. Okay. Let us see. It does. Between what was the numbers? I forgot it. Between 5.5 and 7, okay, you see the disturbance is 5.5 exactly here, and 7 is increasing but is rejecting the disturbance again. So our control is enough robust, enough to strong to reject this ramp disturbance. Hmm? Are you gonna tell me, Pema? You were telling us about a parabolic input, remember? I'm saying 5 even to 8. Parabolic, I'm going to say 0.5. This is parabolic, that's right. Here we go. Yes, from high school, and even I taught you. So it's going to be, let me see, this is parabolic. Here we go. Let us see if it rejects it. Okay, here we go. Okay, so it's parabolic. We find once parabolic. See? Okay, it's rejecting that. But I have to give more time for that. Let me go probably 50 seconds, 15 seconds. It takes more time to reject the disturbance here. See? Here we go. And finally it goes to 0 here. Error signal. Error signal. Here we go. So it says what I tuned, okay? Rejecting any sort of disturbance. See what I'm saying, everybody? So for making more general, because I'm going to share this file with you, I'm going to say between 1 and 3 is a step. Else if between 4 and 6, I'm gonna make it as ramp. Okay, ramp disturbance, and between 7 and 8.5, I'm gonna make it parabolic. Else, there's no disturbance. Here we go. Let's see what's happening. Oh, see, the first control signal trying to compensate. Second, third. Here we go. First, second, step. What was the 4 and 7? Let me show you. First, fourth, and 7th. There we go. But finally rejected all disturbances. Now let us see. You remember that I taught you. I taught you 5 input to the system or disturbance to the system. Remember, impulse, step, ramp, parabolic, and what was the last one that you plotted? Body plot. Harmonic, that's right, frequency response. Now I'm saying, you know what, I don't want to do it. Else, instead of this, I'm going to say, let us say D is sine of T. A harmonic disturbance, persisting harmonic. And the amplitude is 35, say, just curious. Let us see these gains that I tuned after the class. works well on this reject disturbance. Oh, guys, look at it here. Got the control input that tries to remove that. And finally, yes, goes to 0 again, finally. Huh? What was that? 7. 7. Yeah, it rejects disturbance. Okay? Even that rejects disturbance. Okay? But let me increase the frequency to make it visible. 20T. I want to see if it works. Oh yes. Oh yes. Do you see, guys? I apply the disturbance here. Frequency with high frequency. Finally goes to 60. Let me make it bigger. High frequency. I don't know, 50. And this is 60. There we go. Between minus 1000 to minus 13. 1000 between and minus 1300. So again, I'm assuming that your actuator range is can tolerate this. Okay. If not, we have to change these gains. Okay. So here we go. Error signal, and you see the high frequency. See high frequency, and finally goes. Now let us. Now you know that you can do that. Let me make a movie of this. Oh, before going that, this is linearized. See, GM. Now let me do for nonlinear. I'm gonna say what's the difference between linear inverted pendulum and nonlinear that you have from previous class. That's right, the sign. This is nonlinear inverted pendulum. Non-linear inverted pendulum. So you have to change the state variables. 3, 4, 4, and this is gonna be 3. Once you did it, so you have to change everything here, guys. Let me write here. These are for linearized ODE. Now you have to change all of this and make it for what is that? Oh, for nonlinear. For nonlinear ODE or nonlinear. You have your notes from the previous class, remember? So here your E, I'm gonna say E nonlinear, and this is gonna be M3. And this is nonlinear. This is gonna be M4. That's right. Now you know it. I don't want to repeat myself. N gonna be N. I'm just adding N's. N nonlinear, and U for nonlinear inverted pendulum. Nonlinear inverted pendulum. And U1 N for nonlinear. N. Okay. And I want to plot this. It's gonna be N. Here we go. You got it, everybody? So U1. But I'm going to keep the disturbance the same. Okay, I don't change it. So here, if I want to plot TP, no, UP for nonlinear, I have to put this nonlinear here. And also this, we have nonlinear because I'm going to make a vector of that, like as previous case. UPN, that's right. Where is that? No, UPN. Okay, now you have it. So UPN. And now we have this also here. Where did I that after ET UPN UPN and this, because I wanted to plot error signal and the control command. Now I have to come here, say hold on, this is error signal, obviously this is for nonlinear, and I'm gonna make a legend. This is for linearized ODE. This is for nonlinear error signal based on that PID. Okay, and I'm gonna do the same here for control input. And hold on. And this is N and the red. I forgot to put here red line. We got that. And now here we have, this is for only teaching purposes. Hold on, I'm gonna plot the inverted pendulum angle, nonlinear, 3 R, and again a legend. Here we go. Okay, so where we are, let me double check everything. Okay, these errors and U are for linearized ODE. And now let me go, because I'm going to share this with you, R for nonlinear ODE. So I'm going to just lump these together to avoid. Here we go. So E1, E is M3, M4, and now N is E1N, and this is E1, E1, and E1N. Yeah, that's right. It's good. Okay. Now we comment it. When you graduate, guys, and you're an engineer, even if you go to grad school, your code gonna be huge, even in Python. You have to comment it, because after a while you're back, you don't know what you have done. That's what I'm doing with you. I'm gonna share with you. So I want to see, I apply the same PID to linearized and nonlinear inverted pendulum. I want to see what's the difference between them. So something is wrong. What's wrong? Oh, UYN. I'm sorry. See? Always double check, because this is UYN. There we go. Do you see, guys? This is the control command, linearized, and very slight changes. Let me just magnify it. Zoom in. See, very slight changes, guys. Very slight. And this is error signal, almost the same. And if you want to see this, here we go. Very slight changes here. Okay. So you see, the linearization works well. It didn't work in the previous version that we designed based on zeta and omega n, but when we changed the gain, it worked. Okay, see, very slight difference, guys. So the blue is linearized and this is nonlinear. You got it, everybody? Now I want to make a movie of this, because eventually you have to make a movie, and eventually you have to put on the real-time toolbox when you connect to the real experiment. What I'm gonna do, I'm gonna say size of this vector is the length of theta 1. Let's see what it gives to us, guys. Look at here. It's gonna give us a number. So this angle, either linear or nonlinear, theta 1, that's right, or linear, has a size of, a vector has 1501. Why I'm doing that? Because I'm going to put in a for loop, or I'm making movie of that. I'm going to say k from 1, first element of this vector, and to the last, to the size. Here we go. Okay? And, oh my God. And now let me go back to the notes, because I have to teach you a little here how to make a movie of that by coding. Now you design controller, you want to see how it works in reality. Huh? Guys, I wanna plot this. I wanna make a movie from here, guys. This, okay, and a circle here, inverted pendulum. If we design a controller, it's gonna show exactly comes as it shows. A disturbance here, and finally comes here. Exactly, I'm gonna show it to you today by movie. Okay. So here, this is maybe, you know, you were in my vibration class. Even that you are not, I was teaching in the vibration class. Okay. So this is how we plot a line in MATLAB. We say figure 1, plot x of this point. I'm going to say x of this point is 0. And x of this point, if here is L, going to be L sine theta. But your theta from MATLAB code is this, right? Your theta is this, ODE. That's right, for linear I'm talking about. So it is 0 and sine of, I'm just putting here first element. But here we are putting in the loop, for loop. So you have to put k. In each loop, it's gonna read that theta. That's right, each loop. It's very easy. You got it? Now the y's of this point. Y of this I'm gonna put again 0. And the y of this point gonna be L cosine theta. From vibration or high school trigonometry. So it's gonna be 0 semicolon cosine k and 1. Bingo. This is plot. Then I'm gonna say, hold on. I'm gonna plot this. This is square. How we do that? Because if you know my vibration lines, you know it. But if you don't know, it's gonna be helpful for you. Not for this problem, for very complex making movie based on the control dynamics. You have to write like this, guys. There's a command as a fill x of a square, y of a square, and say black. So x of a square, you have to go clockwise. Oh, sorry, counterclockwise or clockwise. You cannot go random. You have to say exactly. I'm going to type in this MATLAB. I'm going to say x of this square. It's gonna be. I'm going to go this way. This. But I'm going to make it at the middle. Here is 0 and 0. So if x gonna be minus 0.1, here, 0.1 minus 0.1, and corresponding y underline s, again minus 0.1, minus 0.1 at the same elevation, 0.1 and 0.1. Put it here, it's gonna plot it for you. Don't worry, because I'm gonna type in MATLAB now. Don't worry at all. So we derived the equation of the motion, we linearized, we did everything, we designed controller, we applied the disturbance. Okay. Now I'm gonna say, first of all, we need the length of the disturbance, L sine theta. So we defined here L. Now we need L. Here we go. L comes out. I'm gonna make it a global parameter, and the same here, L. So I'm gonna say figure 4, because we have figure 3. Figure 4. Now I have to say this for line 0 L sine k, exactly as I told you, and 1. This is x's and y's for line, and this is exactly this. Here we go, cosine. So in every k that is correspond to the size of this, it's gonna replace here, that's right. And I'm gonna make it blue, this line. And I'm gonna make font size as 2. I'm sorry, line width, not font size. Line width is a command in MATLAB. Here we go. And line color is blue, line width 2. If I end here, guys, just hold on with me, okay? Bear with me. Let me double check. Yeah. Let us see what happens. Oh, what's wrong? Put this here. What's wrong? Let me guys, I'm sorry. This is theta. Theta sine. Why I typed this like that? I'm sorry, guys. Theta. And this is k here. Oh my god. And cosine. Oh my god. What I have done this. So guys, L sine of theta k and 1. Yes, this is true. Oh my god. I don't know why I have done this. L cosine theta on 1. Right? And do you have extra term here? Yes. So if I run this, do you have extra? Oh, yeah, I have extra here. Okay. What's wrong with this? Okay, this is closed. And this is closed. Right? Hopefully. Yeah. See, it's showing coming down, but it's not visible. Okay, why? I'm gonna tell you why. Because you have to put the axis, guys. I'm gonna show you. You have to say axis x from minus 0.2, 0.4 to 1.6, and y is minus 0.5 to 1.6. Here we go. Now we can see that. Here we go. So that, guys, you see that? It was disturbance and goes here from 90, see? There it is. Disturbances and back to 60. So you made that. Now let us make it complete. I'm gonna first say line width is 2, and then hold on. Now I'm defining x of s, x of square as a base, as I said 1.2 1, 0.1, 0.1, and minus 1.1, and y of square as the base of the pendulum as minus 0.1, minus 0.1, 0.1, if you look at your notes, and 0.1. Here we go. I just defined about that for. So here I'm going to say fill x of s and y of s and let I say green. Here we go. Oh, not this. Okay. Here we go. Oh, maybe this is running. Oh yeah. Okay, guys. Good. But you see, it's like as the name of this in the simulation in the mechanical is stick diagram. Stick diagram. It's technical name. We don't want to have it. I want to have a movie of that. I don't care. So what I'm gonna do, I'm gonna say after this hold on, you have to type hold off. For the next for loop, you have to hold it off. Here we go. Okay. Here we go. Those are disturbances. See? Sine disturbances as I applied. It was oscillating. And finally go back to 60 degree from here 60 degree. To give you a sense of what is the reference, I'm gonna say plot 0, 0 and 0 and 0 and L for the upright position. I'm gonna say blue and just doing this. Just doing this and to give a measure of that. Hold on. So based on the control, you did it. See, from here 60. There we go. Disturbances. Controller tries to remove those sine disturbances and backs to 60 degree. There we go, guys. You did it. Yes, everybody? Interesting, right? Okay. See the disturbances. And now you can put a grid on that again. You can say grid and put a text here. Put a text. You're gonna have to give me time for the text because I want to do some magic. Okay, text is say 0.5 and 0.6, and I have to search this because I have done this a while ago. Num to Spring text. I'm gonna surprise you. Let me search for it. Let me first. Okay, so I'm gonna say text is this. I'm gonna say theta of t equals to, I cannot believe it, what I'm doing right now. This, for linearized obviously, multiplied by 180 divided by pi. This and this, hopefully it works, huh? Theta of, hopefully it works. Let's see what it does. Oh, shows the real-time angle, guys. It says it still is rejecting the disturbances, see? Finally goes to this oscillation and now very close to 60 degree. There we go. Going to 60 degree eventually. Okay, 60, 60, 60, 60. Here we go. You like it, guys? Yes, if you come to my classes, you're gonna learn this. So, but I can also, because I'm gonna share with you to be proud when you graduate, you can use the relating interpreter to make it sexy. You can say, hopefully it works. LaTeX, so it's gonna plot this. Yeah. So, and I'm gonna move this a little upper, say point, and I'm gonna make this as 8. And bear with me. Hold on. Text, another text I'm gonna make. I'm gonna say at 0.7. What I'm gonna do, that's enough. First, I'm gonna say, I think I have to say color is 100. If I'm not wrong, so let me see. Here I have to write it down. Color. Not, hold on. Let me see if it works. Yeah, I changed the color. There we go. The red, this is the code of the red color in MATLAB, 100. I remember when I was PhD student, okay? Okay, I don't care about this. I wanna see why it didn't work. Oh, because I have to put like this. This is the, see, I taught you in the beginning of the semester, you have to put on this $2. Now, if you do that, okay, enough. Where is that? Okay. And let me, grid, because I'm going to share with you. Let me put this at the middle of the page. One. Now run it. Here we go, guys. See, very professional data. Here we go. Still, we have disturbance. It's 65. Remember that we're applying different disturbance to the system. Eventually overcomes that. And oh, you can also do this, guys. To make sure for which second you have disturbance, I want to do this. Sorry, guys. Bear with me. Hold on. I'm gonna say text. Put above this, say 9.5. Here, I'm gonna say time of operation. And this is T. This T, guys. Here we go. This T. Time. Here we go. And just change color for this. We're having fun, huh? I want to see in which time you have such a theta. Oh, okay. Oh, this is green. See, this is very invisible. Sorry, guys, I have to fix it. Okay, so let us keep it that as same 0. And this is too much. 9.5. 9. Here we go. See, these are not even 1 second. Now we are going to 2 seconds. I forgot the time of disturbances, okay? See, these are disturbances yet. Between 2 and 4 and 4 and 6 and 8 and 9 probably. See, these are seconds. And that's why you are in 59. And eventually, you see, it's going to go to disturbance, sine disturbance, harmonic disturbance. Bear with. See, that harmonic disturbance was between 7 and 9 probably, right, in the code? See, this harmonic disturbance, rejecting that. Okay? And finally, settles down at 60. You got it? Everybody? There we go. Now you are a control engineer. Have a sense of damping, have a sense of stability, and now you know how to tune the gains. If you take the P gains to a high value, I don't need you, to a high value, it's a high gain controller. It's gonna increase the amount of torque to the actuator. We have to consider that to avoid saturation and overloading the actuator. Then you can tune based on requirements. You want to have settling time for 9 seconds or settling time for 55 seconds. For example, I was working for the US Navy on a project that the settling time must be 60 seconds for the valves. 60 seconds. You're going to ask me why? Because if you close the valves very rapidly, it's going to generate a cavitation. I hope that you read that in the fluid mechanics. And a cavitation over time gonna break the valve. So it depends on the application you have. See what I'm saying? And then you can make a movie from this and playing your computer. Okay? I may teach you the next class before going to Nichols Ziegler. Nichols Ziegler to me is very funny criteria. I have to teach you because I'm a professor of you. Because these are very, very special cases. Very, very special cases. But I'm going to teach you. And we are done with the PID control.